All right, so I want to go take a second here, like more in a second, to go through some of these problems here. Just make sure you're good on 6.5, 6.6 before the quiz. So, expanding problems, so we're going to use your three properties. You're either going to be converting them to addition, subtraction, or you're going to be moving the power out front. So, this is a good example of one that when you have a product in here, you change it to adding two separate logs. You can then also take whatever powers you have, like the 4 and the 7, and you can move them out front like so. If you have a division problem, like let's say this one, for example, so this is log of x minus the log of the 7 minus the log of the y, because you have two separate parts down here. This one, there's only one part, so we got log of a, and then log of b, and you can go ahead and take the 2, move it out front. So for all of those, you're really just doing that process with whatever you're given. Down here is the same thing in reverse. Writing it as a single log, you're taking the expanded, you're going to move these back to being powers. You're going to write this as division, and then just simplify it as much as you can. If it's addition, like right here, it's going to be 2 squared. This is going to be 2x to the 5th. You're going to change it to being a product. And then I just went ahead and simplified it because that's a 4 and 2 to the 5th is 32. So I did 4 times 32, got the 128. But that's the idea with those problems. It's just the opposite of the previous section. 13 is just like the one from the notes. Take this pH, substitute it into the formula we created, and you can find the number of moles per liter. And then pretty much just wraps up with change of base, which is anytime you want to do a different log, if you want to type it in a calculator using change of base, you can do log 10 over log 2. In other words, it's always log of the argument over log of the base. You can use natural log 2 if you want to, but that's all I did with these. Pay attention to how you're supposed to round. Be careful with that. These ones, once you rewrite it, so like this is log base 4 of 20 equal to x, you can just change a base this. So I did log 20 over log 4 to get that answer. Hopefully change base, feeling pretty good for you. Definitely not too tough. This one, I showed why they weren't equal. So I worked this out and I got 0.63, which is not the same thing as 0.66. The reason why it doesn't work is natural log is changing what these are. It's an operation, so you don't have the same ratio. You can't just cross off ln and call it a day. It's an operation, which means these have different values than just 2 and 3 will have. Okay. All right. 6.6 is definitely the tougher section of the two because now you're putting all these properties to use in solving. So this section here is kind of tough because it is a mixture of all random kinds of solving problems. And some are super easy and some are tough. Like, for example, there's just a plain linear problem on here where you just divide by 4 and boom, you got your answer. I had just skipped these two. These are ones we haven't really learned ways to solve these yet. I guess we could, but they're a lot more difficult than what I'd like. So I didn't want you to do those two. So hopefully you read that in the instructions. Some of these, though, are change of base. Not change of base. Common logarithm. Like right here. When you can convert these to a common log, like this is 3 to the negative 1, and this is 3 squared. Distribute, set equal, and then solve. Those are, in my opinion, the easier types. Any of these where you have a common base, or you can create a common base. This one's another one. All of those are going to follow like that example 1 from the notes. And then you hit ones where they don't have a common base. Ones like 8. So I subtracted this 4 over to isolate the exponential. And then this one I just did my log rule. So I said log base 3 of 11 equals x minus 5. So this is kind of using my solving skills back from 6.3 and 6.4 and solved it that way. This is just a number, added the 5 over, got my answer. Some of these you need to solve by logging each side or writing it as a base. So there's all different routes you kind of need to take in these cases. And that's sort of how these solve out. Natural log, just to remember, you could write this as natural log is e to the 5th equals x plus 1. Then we move down to some of these other solving ones. These are like what we practiced in the 6.6b section where, okay, now we know since these are the same exact logs, we can set these two parts equal to each other and then solve what we're left with. That's a pretty easy example. Some you end up with a quadratic like this one where you get x squared minus x equal to 2x minus 2. You move everything to one side and then you solve it by factoring it. So yes, you got to remember factoring from, all of first semester, part of this semester. Factoring really never goes away. This is another one you could do by factoring or by just recognizing that it's a square root. So that's why I got plus or minus 5. One of the things I did want to talk about with this is that in the assignment, when you did some of these problems, they talk about extraneous solutions. And there weren't any of the notes and there weren't any on here. But the idea is when you go back to check this, let's pretend this had been a -3. So let's say you solved this and you got -3 and that was the right answer. Like we didn't mess anything up. That was right. But if you went to sub this in and you put a -3 in here, you'd be trying to log a negative number. And that causes an error, causes a no solution. That's that concept of an extraneous solution where you solve for something, you did it right, but it's giving you a no solution when you input it. It's not a huge concept in these. That's why we didn't really go over many. I think I threw a couple on the OTI, not really intentionally, but I kind of realized they were on there once I sent it. But yeah, it is a thing that can happen, but none of these did that. All of these, if you plug them back in, they do show that they work. This one, you plug in 5 here, or you plug in -5, it'll work both ways. All right. The next piece on here was solving by graphing. And this one I don't love. This one is really crunched in here and it's hard to see. But once I graphed them in my calculator, I just found my intersection and it was at 1.353. With that, so as far as your buttons go, I don't have the equations in there, but it's second calc, and you want to pick intersect. Or if you're using decimals, obviously you can click on the intersection point. But you want to pick your intersect, and then you're going to press enter, enter, enter. I don't have a second equation in here right now, so let's just pretend I did. Let's say it was like this. So if we had something like this, we'd want to be able to find that intersection point, go over to the one you want, and go enter, enter, enter. And then it'll hop to it, and it'll give you the value. Obviously, this was a different problem, but that's all we need to do to be able to get those intersection points. And sometimes they cross twice, sometimes they cross once. You just got to look at the problem and see where the intersections are. Like I said, I didn't love this one. The ones you'll see on the assignment, or sorry, the quiz, the test, are going to be much better visually. This one is tough to see, especially on the graphing calculator. It's really crammed in there. It doesn't work great. What else we got here? We got 21 is kind of a good just sort of tying everything together in this chapter problem. So you have 700 bees on September 1st. Winter is coming, Game of Thrones style. Number of bees decreases by 35% every 2 months until March 1st. How many bees are at March 1st? So if they're losing 35%, they're keeping 65%. So I wrote this little exponential equation here. Start with 700, keeping 65%. And then I had to figure out how many time periods this was. So starting in September, which is the 9th month, you go ahead 2 months, that'll be 11, which is November. You go ahead 2 more months, that'll be January. Then you go ahead 2 more months, that'll be March. So it's 6 total months, which is 3 time periods because it's every 2 months. So I went ahead and evaluated this at 3, and that's how I got that there'd be 192 bees remaining. You don't really have to use logs at all in this case to solve this problem. This one is really just kind of a general exponential style question on here. So more or less just to remind you of some of the stuff, but not necessarily super relevant for the quiz, more for the test. So yeah, hopefully you're feeling pretty decent on this stuff.